Let's consider, for example, a lake, a pristine lake with lots of species, clean waters, high diversity, and so on. Imagine now that we increase nitrogen in this lake. At the beginning, nothing happens. We keep introducing more and more nitrogen, and it seems that this doesn't affect the lake. However, once we reach a critical point, slightly increase in the amount of nitrogen is going to change completely the state. We'll move from that pristine lake to one characterized by a much lower diversity of species, turbid waters, dominance of a few species. There's been a huge transition. This is an example of big changes in ecology. These changes are not smooth, are not linear, but we reach these points in which there's a sudden shift to a contrasting state. One of the challenges we are facing right now in relation to global change is trying to anticipate the existence of these critical points before they are reached. Let's take an ant isolated from its background. It's certainly quite a simple object. Its repertoire of behaviors is quite simple. We can conclude that there is not that much that can be done by an ant. However, let's now consider the entire society, an ant society, and now the situation is quite different. This society is able to compute, for example, it's able to choose among the optimum search paths to food. It's able to create large-scale structures like an ant nest, and obviously this is a property, an emergent property that cannot be explained on the basis of the simple repertoires of behaviors of an individual ant. Well, evolution plays a key role, as the famous geneticist Theodosius Dobzhansky once wrote, nothing in biology makes sense but in the light of evolution. I think that phrase encapsulates that evolution is the way to explain all type of ecological and evolutionary processes. There's different mechanisms such as mutation, natural selection, genetic drift, species sorting, and other mechanisms, and all of them in combination create this dynamic scenario in which we are able to explain the huge amount of diversity that we observe right now on Earth. Heterogeneity plays a major role, and to understand that, we have to move on from the domain of equilibrium systems to fully embrace this non-equilibrium situation in which biology takes place. For example, in equilibrium systems, if we deposit a drop of ink into a glass of water, we'll see how this situation is going to be homogenized through time. That is to say, we'll end up with a situation in which all water looks pretty much the same. Thus, it was very difficult to understand biology from that perspective. And the reason is not that biology defeats physics, but we have to change our paradigm. We have to consider non-equilibrium systems. And that under that situation, we can fully embrace this process by which fluctuations now play a major role. There's symmetry breaking, and these small fluctuations play a major role in the sense of canalizing the system towards one direction or another one, both in time and space. Biological systems, as other open, far from equilibrium systems, have this dialogue between order and disorder. On one hand, disorder is encapsulated by these fluctuations we were talking about. These fluctuations play a major role because are the way by which the system can go from one contrasting state to another one. On the other hand, at the end, there are these boundary conditions that allow the emergence of order structures such as the ones we see through development. We're going from the most simple, an egg, to the most complex, an individual. And this process should be understood through this dialogue between order and disorder.